Hello, so this is my second video for Unit 6, and we're going to look at spring combinations. The first one I'm going to talk about are spring combinations in parallel, where we have two springs attached to the same block, and we call it parallel. We have them in series too, so that they actually take on some vocabulary that we talk about in terms of electricity. But in this case, right here, I've got two springs holding the block in parallel here, and when the springs are in parallel, I actually take their K values or their spring constants and add them together. Now, for springs that are in parallel, we recognize that the displacement has to be the same for both. So when I'm looking at this right here, like the spring constant or the force being applied to the first spring and the force being applied to the second, if the x is the same, then we have to add K1 and K2 together. So notice that this equation is in black, which means that it is not on your laminated sheet. So it is something you have to kind of keep in mind. When the combinations are in series, so they're attached to each other one after the other, like this, then we have to do something a little bit different because their displacements won't necessarily be the same. So one spring, the first spring may displace a certain amount, and then the second spring may have a different amount then. And because of that, we have to actually rearrange this. So what we get is the force is going to be the same. So I rearrange that, or I take that out. And so then to get my total spring constant, I get 1 over the spring constant for the first one and 1 over the spring constant for the second. So this is a little bit different than we found in the one with parallel. So overall, if I want to know the overall spring constant, and notice that I take 1 over K1 plus 1 over K2, and however many springs, that could be 3, 4, or more, then whatever answer I get, you're going to have to also take the reciprocal of it again, because that equals 1 over the equivalent spring constant. All right. So we're going to take a look at example problem number 4, and it's another one of our ranking problems. And it says, rank the spring block oscillators in the diagram below from highest to lowest in terms of equivalent spring constant. Okay, so this one right here. Well, I know that my ones in parallel are going to be highest because these are the ones where I just add the spring constants together. So this is 10 plus 15, so this one's got 25. And this one is 10 plus 10, so this one is 20. Now, over here, though, for my A and C, this is when I have to take 1 over 20 plus 1 over 5. And whatever I get, I then need to take 1 over, or take the reciprocal of that answer. So for A, I got 4 Newton per meter. And for C, I get 7.5 Newton per meter. So by ranking my spring constants, I'm going to get B, D, C, and A. Now the period of oscillation is simply this equation that we looked at in the first video. The period is equal to 2 pi with the mass over K. And in this case, because I have a combination of springs, then I'm going to use my equivalent spring constants that I have right here, and those were all newtons per meter, and simply plug them into the equation that I have here. So for my spring constants, for my periods of oscillation, for A, I got 5.44 seconds. For B, I got 3.07 seconds. For C, I got 3.24 seconds, and D, 2.81 seconds. Again, as before, I encourage you to pause, try these out, make sure that you're getting the same answers that I am, and then your final ranking should be A, C, B, and D. And please let me know if you have any problems or have any questions with that. I'm going to do 2 more example problems in this video, but I'm going to change things up just a little bit. I'm going to change our springs so now they are hanging or vertical spring oscillators. A spring block oscillator that can be set up vertically, gravity is going to pull this mass down. So, well, let me back up just a second. So if I have a spring attached and it doesn't have anything else attached to it, it's going to have its own equilibrium, right? And I could stretch this spring down by pulling it with a force and stretching it even more. Or I could just attach a block to it like I have here. So once I attach a block, the spring itself is going to stretch a little bit to compensate for the force of that block. So it's going to pull it down with the force mg, and then that also means the force on the spring is going to be equal to ky. So I'm going to call the downward positive, and its equilibrium position, at its equilibrium position, we're going to say the y is equal to y equals EQ, or our equilibrium position with y. Now, when we start working with problems like this, oftentimes we are setting the potential energy of gravity equal to the potential energy of the spring. When this is maximized is also when my potential energy of the spring is also maximized. So at equilibrium, we would say the force that's being applied here, the mass times gravity, minus the potential energy of the spring is equal to 0. In other words, I can set these two equal to each other, the mass gravity and the potential energy of the spring. So if I want to know the y at equilibrium, I just set up my mg over k. If it's not at equilibrium, so let's say I've applied the mass and the spring is stretched, and now I'm pulling on the mass and pulling it even farther down than it was on its own. So I'm going to take this mass, I'm going to pull it downward and create an even bigger change in the change in y. In this case, and I kind of wrote it out here, and I was going to try and make this kind of quick here, but the force net is equal to the mg minus the k and the distance of the y plus the amplitude in which I stretched it. So this is the stretch that I added to the mass. And I'm going to set that equal then to the mg minus the ky, or in other words, the force of the spring minus the force that I applied. So that's one way we can kind of set those all equal to each other. So the force net, and I finished this off here, the force net is equal to negative k times the additional amplitude. So you might be thinking, why did I even go through this? I wanted you to see that once I attach this block to the spring, I can readjust the equilibrium. In other words, it's not going to really matter that what the displacement was once I added the mass. If I just basically moved the change in y down a little bit. So instead of the spring maybe stretching here to here, now that I've added the mass, now it's stretching from here to here. And so now I'm really just paying attention to this additional amplitude that I applied to the block. So to analyze the vertical spring system, I find the new equilibrium position of the system, taking into account the gravity and the mass of the block that's being done, or that's being added. No need, you don't have to continue to deal with the force of gravity. In fact, once you just take that into account and adjust the equilibrium position, you treat it just like a horizontal oscillator. So we've seen problems like this before. So let's take a look at example problem number 5. I've put a 2 kilogram block onto a vertical spring here, and the spring constant is 200 newtons per meter, as shown in the diagram here. It says determine the period of the block's oscillation. Well, since I am just taking a look at I'm not looking at the difference of the spring without the block. I'm only looking at the spring with the block. So I can set it up just like a horizontal oscillator. So my period is 2 pi square root of mass over k, where k is the spring constant. So I've got my 2 kilograms on top over my 200 Newton per meter, and I take a square root there, and I get 0.63 seconds as the period. Now the second part of this question says, what is the maximum displacement of the block from its equilibrium while undergoing this simple harmonic motion? So this one's a little bit more complicated, so actually I'm going to go back and erase this. Give myself a little bit more space here. I'll go with red this time. All right, so the potential energy of gravity is equal to the potential energy of my spring. So I'm going to expand on this. mg change in y. So the distance that the mass changes is equal to 1/2 k. I'm going to use change in y instead of x, just because we're moving in the vertical rather than the horizontal. So I'm going to set that equal to the potential energy of the spring. So now, if I want to know displacement, I'm going to simplify this equation a little bit and basically solve for y. So I'm going to cross one of these out, get rid of that. And so my change in y is equal to, let's see here, 2mg over k. All right, so I can solve for this pretty easily then to get my change in y. And I'm going to get 2 times the mass of 2 kilograms times my gravity all over my spring constant of 200 Newton per meter. And when I get this answer, I'm going to get 0.2 meters. Now, keep in mind, this was my change in y. So, but what I want is, if we look at the question, it says, what is the maximum displacement from its equilibrium? So the change in y is actually from the very top of the oscillation to the very bottom of the oscillation. And what it's asking me is basically what's called amplitude. And while we haven't talked about that too much, I know we talked about it in chemistry. Amplitude is from the origin to the crest. So basically I'm talking about this distance right here. So that means amplitude is actually 1/2 of my change in y. So my final answer, I'm going to take this divided by 2, and my final answer is 0.1 meters. So that's just something to kind of pay attention to. Is it talking about the total distance that this block oscillates through, or is it really just talking about how far did it go away from the center? So something to pay attention to when it comes to those problems. And I've got one more that I want to do with you. I have a 5 kilogram block that's attached to a vertical spring. I've got a spring constant there. After the block comes to rest, so in other words, I've added the block and I've let it go, it's pulled down 3 centimeters and released. Okay, so I'm going to pull it down and release it. So my period of oscillation, if you remember, we said that this is going to act like a horizontal oscillator. So my period is 2 pi square root of m over k, and I'm going to put square root of 5 kilograms over my 500 Newton per meter, and I'm going to get 0.63 seconds. Okay, kind of a coincidence. That was also the answer for number 5. B, what is the maximum displacement of the spring from its initial unstrained position? All right, I'm going to start this one the same way I started the example problem number 5. I've got my potential energy of gravity, and I'm going to set it equal to my spring. So I'm going to do mg change in y equals the potential energy of my spring, 1/2 k change in y squared. Remember, this would normally look like x squared on our laminated sheet, but I'm in the vertical here. I'm going to cross out one of my y's, and I'm going to put my change in y is equal to my 2mg over k, which is 2. Got my mass of 5 kilograms times g all over 500 newtons per meter. And this is 0.196 meters of maximum displacement. So if I want to know the spring from its initial unstrained position, okay, that also means I'm talking amplitude only and the additional 3 centimeters from its unstrained position. So the first thing I'm going to do is I'm going to divide this by 2 to get my amplitude. So my maximum displacement is more like 0.1 meters. And then I'm going to add my 3 centimeters, which is what was initially added to this. So basically my maximum displacement is going to be 0.13 meters. And that is my final answer. Well, again, I hope this has been helpful. And please let me know if you have any questions. And we will move on to ideal pendulums next. Thanks.